So imagine you just dropped like $20 million on this state-of-the-art fleet of electric delivery vans.
Huge investment.
Right. Massive. And you've got the vans, you're ready to go, and then your local utility company just turns around and says, yeah, you actually won't have the electricity to plug these in until like 2029.
Which is just a paralyzing nightmare for these
It
companies.
really is, and that's exactly the crisis rippling through the commercial EV industry right now. We are basically trying to slap this ultra-fast 21st century charging tech onto a grid system that's, I mean, fundamentally, it's still running on mid-20th century architecture in a lot of places.
Yeah, and the friction between those two realities is generating the single biggest bottleneck in modern transportation today.
Because everyone just focuses on the cars, right? Like the battery range, the 0 to 60 times.
Exactly, the flashy stuff. But the charging infrastructure itself, like the actual physical connection to the grid, that's where the economics are just quietly breaking down or in some cases completely stalling out.
So to figure out how the industry is bypassing this massive gridlock, we're doing a deep dive into a really fascinating stack of new data today for you.
We've got some great sources to go through.
Yeah, we're looking at the April 2026 fleet analyses by Electrons X, some supply chain briefs from the Alliance for Transportation Electrification, and honestly, a few highly unconventional startup spec sheets.
Highly unconventional is a polite way of putting it.
Right. By the end of this deep dive, you are going to see the EV landscape completely differently. You'll understand the invisible financial traps that basically dictate where chargers get built, the staggering supply chain wars, and the wildly inventive workarounds.
Including, spoiler alert, the highly counterintuitive move of actually burning fossil fuels to charge electric cars.
Which is wild. But before we get to that, we have to talk about why a 2026 fast charging station operates the way it does. And that means looking at the invisible wall every operator hits the second they plug in, which is commercial utility billing.
Oh yeah, the demand charge.
Okay, let's unpack this. Because commercial billing is like nothing like your residential power bill at home. At home, you mostly just pay for the sheer volume of electricity you use, right?
Right, it's straightforward.
But commercial sites get hit with this demand charge. I kind of like to think of it like going to an all-you-can-eat buffet. But imagine you walk in, and because you took one massive, towering bite of food in your first 15 minutes, the manager walks over and charges you 4 times the regular price for the entire month.
Regardless of what you eat after that.
Exactly. Does that analogy track with the data?
It honestly captures the financial hazard perfectly.
Mm-hmm.
The data from the Alliance lays this out so starkly. Utilities measure a commercial facility's power draw in these specific 15-minute intervals.
Okay.
And your demand charge for the month is calculated based on the single highest 15-minute spike during your entire billing cycle.
So wait, if I have a highway charging depot and it just sits completely empty all morning, but then like 3 families pull up in heavy-duty EVs at lunchtime, plug into 150 kilowatt fast chargers all at the same time.
Boom. That depot just triggered a massive localized power surge. And based purely on that single 15-minute window, the station's monthly utility bill can jump from basically zero to over $2,000 in demand charges alone.
$2,000 just for having a busy 15 minutes.
Just for 15 minutes.
I mean, if you're a charging network operator, a random spike in traffic like that just suddenly obliterates your profit margin for the entire month.
Oh, it gets even more brutal when you look at the break-even models.
Yeah.
When you factor in the amortized capital costs, buying and installing a standard 150 kilowatt DC fast charger.
Right, because the hardware isn't cheap.
Exactly. The operator actually needs a steady utilization rate of more than 10 charging sessions per day, every single day, just to cover their costs.
Which is a crazy tightrope to walk. Because you need a lot of people to charge to make money, but you're terrified of them all charging at the exact same time and triggering that penalty.
Precisely. It's an incredibly difficult orchestration.
So, okay, the logical move for a fleet operator or a network would just be, pay the utility to upgrade the grid at your location, right? Pay them to trench a bigger line, put in a massive transformer, and give the site enough overhead so those spikes don't trigger the penalties.
In theory, yes. Absolutely. But in practice, the supply chain and regulatory delays are just creating a complete brick wall right now.
Right. I was reading the Alliance for Transportation Electrification brief, and they mentioned grid interconnection for new commercial depots is taking, 12 to 36 months?
Anywhere from 1 to 3 years, yeah. And it's not even just bureaucratic permitting delays holding it up. The physical hardware required to upgrade a site, It's just simply not available.
The hardware lead times were staggering. I saw that basic 200 or 400 amp electrical panels have gone from a 42-week wait to 68 weeks.
And that's just for the basic panels. The high-voltage switchgear, which is like the critical nervous system for managing massive power loads at a multi-charger depot, that used to take about 3 months to procure.
Yeah.
Okay.
The current data shows lead times for those stretching out to 12 months. And the costs are soaring, like 4 to 10 times higher than historical baselines.
Which raises a really huge question for me. Why is there a sudden, massive bottleneck for industrial electrical equipment? I mean, transformers and switchgear aren't exactly brand new technology.
No, they aren't new at all. But they are suddenly caught in this massive crossfire between two booming industries. The EV infrastructure rollout is competing directly with the artificial intelligence boom.
Oh, wow. Of course, the data center.
Exactly. These hyperscale data centers being built out to train AI models. They require the exact same heavy-duty, high-voltage switchgear and step-down transformers that a megawatt EV charging depot needs.
So the global supply chain just literally cannot manufacture the raw copper and specialized components fast enough to feed AI and EVs at the same time.
It's a total bottleneck.
So if the grid is effectively a brick wall, parts taking over a year, costs skyrocketing, utilities taking up to 3 years to hook you up, how are the major players adapting? Because they aren't just giving up.
No, they're definitely not giving up.
Like, ChargePort just released this new unit in April 2026, the Express Solo, and looking at the spec sheet, it really seems like they are just trying to brute force their way through the bottleneck.
The Express Solo is a really fascinating piece of engineering. They're billing it as the world's fastest standalone charger for mass-market vehicles.
Okay, so how fast are we talking?
We are talking about a unit capable of delivering up to 600 kilowatts. To put that in perspective, that is enough power to run hundreds of homes channeled directly into a single vehicle, or it can be dynamically split across up to 4 EVs parked around it.
That's insane power.
Yeah, and they've managed to achieve a 40% higher power density. So this massive power output fits into the industry's smallest physical footprint, making it perfect for tight urban convenience stores.
And it uses that Omniport system, right? So it natively handles both the Tesla NACS standard and traditional CCS connectors.
Exactly, so the driver doesn't have to fumble around with adapters.
Okay, but here's where I need you to explain the physics to me, because we literally just established that the grid is completely maxed out, right?
Right.
Taking 36 months to get enough power for a standard depot. So how on earth does ChargePoint drop a 600 kilowatt megacharger on a random urban street corner without instantly melting the local neighborhood transformer? Or, triggering astronomical demand charges the second someone plugs in a Hummer?
It's a great question. And the answer lies in what is hidden behind the charger. ChargePoint actually partnered with Eaton, which is a massive intelligent power management company, to redesign the architecture of the station itself.
Oh, okay.
The Express Solo is fundamentally not designed to pull its maximum 600 kilowatt load directly from the local grid in real time.
Yeah.
They built it as this future-ready energy platform.
Which means what exactly?
It means it has direct DC power input capabilities designed specifically to integrate with on-site solar and bidirectional battery storage.
Got it. So they are co-locating a battery energy storage system right alongside the charger itself. So the charger isn't just a hose hooked directly to the city water main, so to speak. It's got its own massive reservoir tank sitting right next to it.
That is the exact mechanism.
Yeah.
From a grid perspective, this technique is called peak shaving.
Peak shaving.
Right. The site's battery system slowly, steadily sips power from the local grid during off-peak hours, usually in the middle of the night when electricity is cheap and abundant.
And so the local transformer barely even registers the draw because it's so slow.
Precisely. Then at noon, when 4 EVs pull up simultaneously and demand a massive 600 kilowatt surge of fast charging power, the Express Solo pulls those electrons from its own battery system, not the city grid.
Man, it's essentially financial arbitrage on a molecular level. You're depositing cheap, slow electrons into your battery bank at 2 a.m. and then spending them during peak demand at 2 p.m.
Entirely decoupling the vehicle's massive power spike from the utility's demand charge meters.
It brilliantly sidesteps the utility penalty. But, and there's always a but, I have to imagine the solution is incredibly capital intensive.
Oh, massively. You have to purchase the ultra-fast charger, you have to invest in a massive commercial lithium-ion battery system, and you still have to deal with localized trenching, concrete work, and urban permitting. even with a smaller grid connection.
Right, which leaves a massive gap in the market. Because what if you are a logistics company or a real estate owner and you simply cannot afford the hundreds of thousands of dollars in upfront capital for a battery system and civil engineering?
Or maybe just lease your lot and the landlord won't let you trench through the concrete.
Exactly. If you can't wait 3 years for the utility and you can't afford a mega battery system, what do? Well, you go completely off the grid.
Which brings us to the rise of decentralized mobile power generation.
And this is where the source material gets genuinely shocking to me. Let's dig into Potter EV and their EV power pods. I mean, I literally had to reread their 2026 spec sheet multiple times to make sure I was interpreting it correctly.
It's definitely a paradigm shift.
They are selling mobile trailers and cab-over trucks that utilize heavy-duty propane generators to fast-charge electric vehicles.
Yep. Propane.
Now, I just have to stop the conversation right here. On a purely intuitive level, driving a propane combustion engine to a parking lot to charge a supposedly green, zero-emissions electric vehicle, it sounds like it defeats the entire environmental purpose of the EV transition.
It feels deeply paradoxical. I mean, it sounds like a massive step backward. But when you strip away the optics and dive into the hard thermodynamics and the economics provided in the analysis, it actually presents a highly compelling interim solution for a gridlocked industry.
Okay, color me skeptical, but let's hear the financial math first. How does buying liquid fuel compete with just pulling electricity off a wire?
It all comes down to energy density. 1 gallon of propane contains the thermal equivalent of roughly 27 kilowatt hours of electrical energy.
Okay, 27 kilowatt hours.
Right. Now, if your local utility charges a commercial rate of, say, 12 cents per kilowatt hour, pulling that 27 kilowatt hours from the grid costs $3.24.
Got it.
But in the commercial market, buying in bulk, propane is currently securing for well under $2 a gallon.
Oh, wow. So strictly from a raw energy cost perspective, the propane is highly economical.
Very much so, especially when you factor in that you are completely avoiding those demand charges we talked about earlier.
Okay, so the arbitrage works for the wallet, but what about the carbon math? Because you are still combusting a hydrocarbon right there on site.
This is where the analysis gets truly fascinating, because it forces us to look at how our grid actually generates and distributes power in reality.
Right, because it's not all wind and solar.
Far from it. The expert data points out that roughly half of the electricity generated in the United States is still powered by burning coal.
Wow, half.
Yeah, so when you calculate the aggregate carbon footprint, the U.S. grid averages 167 grams of CO2 equivalent per megajoule of energy.
167 grams, okay.
But conventional propane, when it's combusted efficiently in a modern generator, produces only 79.6 grams of CO2 equivalent per megajoule.
Wait, really? So the propane actually has less than half the carbon intensity of the average U.S. grid connection?
According to the life cycle analysis, yes. And there's an even larger physical factor at play here, which is transmission loss.
Oh, right, because the power plant is miles away.
Exactly. When a distant coal or natural gas plant generates electricity, it has to push those electrons over hundreds of miles of high-voltage transmission lines. And the physical resistance in those wires generates heat.
So you lose power along the way.
A lot of it. It takes roughly 3 units of raw source energy burned at the power plant to successfully deliver 1 usable unit of electricity to an EV charger plugged into the grid.
3 to 1. You are losing massive amounts of energy just in transit.
Exactly. But with a Potter EV unit, the propane tank is sitting literally 2 feet away from the charger. The transmission loss is virtually zero.
That completely flips the environmental assumption. So a propane generator running efficiently in like a grocery store parking lot is actually operating with significantly less energy waste and lower emissions than plugging that same car into a wall socket fed by a coal plant 3 states away.
The physics heavily favor on-site generation when the grid is that inefficient.
That is wild.
And looking at the hardware Potter EV is deploying, they've designed these to be entirely turnkey. They offer a mobile trailer, it's the M180 model, for roughly $279,000.
Okay.
Or they have a self-driving cab-over truck model for $299,000. And they integrate up to 150 gallons of onboard propane storage, paired with heavy-duty Cummins or LG generators, pushing out a sustained 120 to 180 kilowatts of DC fast charging.
And the competitive advantage there is just zero friction. You have zero concrete trenching, zero permitting delays with the city, and absolutely zero utility interconnection wait times. You literally just park the trailer in a spot, turn it on, and you have a fast charging station up and running in 10 minutes.
Yep. And Potter EV is far from an anomaly here. Looking at the 2026 startup watch list, there is a massive ecosystem accelerating right into this off-grid vacuum.
I saw that you've got companies like L-Charge deploying containerized off-grid superchargers for highways.
Right. And SparkCharge is offering mobile on-demand charging as a software-as-a-service model.
Oh, and EV Everywhere is dropping those 5 megawatt-hour mobile battery stations into festival sites and remote logistics hubs.
The market has definitively realized that waiting for the utility grid is just no longer a viable corporate strategy.
It makes total sense. I mean, mobile off-grid pods and battery buffered stations are brilliant for rapid deployment and bypassing urban gridlock. But let's scale this up to the macro level.
Let's do it.
How do we handle massive 24/7 commercial logistics fleets? Because if you are running 1,000 Amazon delivery vans or, I don't know, a municipal fleet of electric school buses, you can't exactly just have a guy towing a propane trailer around the lot every night.
No, definitely not. At the mega fleet level, the architecture requires an entirely different approach. And the Electrons X analysis lays out the golden rule of modern fleet infrastructure, which is charge during dwell, not during operation.
Right. Dwell time being the secret to fleet economics.
Exactly.
Because if a heavy-duty delivery van returns to the depot at 6 p.m. and it isn't scheduled to leave again until 6 a.m., it has 12 solid hours of dwell time.
Yeah, there's no rush.
So slamming that battery with a massive, highly expensive 150 kilowatt DC fast charger in the first hour is just a catastrophic waste of capital. A standard, cheap 7 and 19 kilowatt level 2 charger will easily trickle charge the battery to 100% by morning without stressing the grid at all.
Which is exactly why the source material highlights the evolution of the Fleet Energy Depot, or the FED.
The FA, right.
A modern depot isn't just a parking lot with plugs anymore. It is a highly orchestrated, localized microgrid. It involves a really strategic mix.
What kind of mix?
Well, you have cheap level 2 chargers for the overnight shift, maybe a handful of DC fast chargers for trucks doing rapid midday turnarounds, sprawling on-site solar canopies, and massive battery units. But the true magic happens in the CMS, the charge management system.
The software side.
Right, the software acts as the brain. It dynamically routes power based on delivery schedules, battery health, and real-time utility rates.
It sounds incredibly impressive, but also incredibly fragile. I mean, you have multiple vendors, complex software, high-voltage hardware sitting out in the weather. If that microgrid goes down, the entire supply chain halts the very next morning.
Oh, the uptime requirements are absolutely ruthless. And this vulnerability has actually birthed an entirely new sector of infrastructure maintenance.
Like who?
Startups like Charger Help are thriving right now by providing real-time diagnostics and specialized technician routing specifically to keep these multi-layered complex depots online. Because you're right, a software glitch in the CMS can literally freeze a city's logistics network.
Which is terrifying. And this actually brings us to a massive structural dilemma that the industry is barreling toward, especially when you look at the 2026 rollout of robo-taxis and fully autonomous delivery fleets.
Yes, the autonomous dilemma.
Because if I'm operating a self-driving fleet 24/7, I have successfully eliminated the human driver, right? My labor costs just plummet. But when that autonomous pod returned to the depot, it doesn't have hands.
Nope.
So if I have to hire a crew of unionized workers to stand around a charging lot 24 hours a day, physically wrestling heavy liquid-cooled charging cables into the sides of autonomous cars, I haven't really eliminated the labor costs. I've just moved the human from the driver's seat to the charging stall.
The autonomous charging paradox. Real issue. The Electrons X data frames this perfectly. An autonomous fleet is fundamentally not autonomous if refueling requires manual human intervention.
Exactly.
And this exact bottleneck is why the automated charging robot market exploded to a valuation of $81 million in 2025. The industry is rapidly deploying 3 distinct physical solutions to bridge this gap.
Okay, I saw Roxy's leading the charge with robotic arms as the first solution. But knowing how inconsistent autonomous parking can be, how does a rigid robot arm find a charging port if the car is parked like 6 inches off center or at a weird angle?
Well, the key is they don't use rigid pre-programmed paths. Roxy's utilizes AI-driven computer vision paired with soft robotics.
Soft robotics.
Yeah, so the arm has a camera that dynamically scans the side of the vehicle, identifies the standard charging port regardless of slight parking variations, and actively guides the plug-in.
That's pretty smart.
And they are entirely retrofittable, meaning the autonomous vehicle doesn't need any special hardware. The robot simply acts as a highly precise human hand.
Okay, what's another option?
Another variation is wall-wart charging. They rely on overhead H-shaped tracks, dropping a robotic charging arm down from the ceiling directly into specific parking bays, which keeps the ground completely clear of obstacles.
But anytime you have robotic arms with servos and moving parts, you have mechanical failure and high maintenance costs. I noticed Wybotic and inductive E are taking a completely different route with wireless charging pads.
Yes, inductive charging.
You just park the autonomous vehicle over a giant pad embedded in the concrete, and it charges through magnetic resonance. But doesn't scaling up, like a wireless phone charger to the size of a vehicle, generate some massive physical drawbacks?
The physics of inductive charging are definitely a double-edged sword. On one hand, you eliminate all moving parts and physical wear and tear. The vehicle simply parks and charges.
Sounds ideal.
But the massive trade-off is the air gap. Transferring high-voltage electricity through the air creates magnetic eddy currents, which generate significant heat and result in much lower energy transfer efficiency compared to just using a direct copper cable.
So you're wasting power.
Exactly. The power limits are stricter, and the wasted energy costs scale up aggressively when you're talking about a massive fleet.
So we have complex robot arms, and we have slightly inefficient wireless concrete pads. The third solution on the watch list seems to completely flip the script on how we even conceive of a parking lot.
The mobile charging robot.
Yes.
The Ion Dynamics Flashbot is the prime example here. Instead of forcing the autonomous vehicle to navigate to a fixed charging stall, the Flashbot is essentially a 60-kilowatt battery on wheels.
It's literally a giant robotic power bank roaming the parking lot.
Precisely. So when an autonomous fleet vehicle enters a geofenced depot and parks literally anywhere in the lot, the CMS signals the Flashbot.
Okay.
It dynamically pathfinds across the asphalt, avoids obstacles, drives right up to the parked vehicle, and initiates the fast charge.
Oh.
It requires zero trenching, zero designated charging bays, and zero civil engineering.
That is an absolutely wild visualization of where we are heading. So if you are listening to this right now, whether you are prepping to transition a corporate fleet, analyzing investments in the energy sector, or you just want to understand exactly why a massive propane trailer is actively charging a Porsche Taycan at your local grocery store.
You now have the insider mechanics.
Exactly.
Yeah.
You understand the crushing financial gravity of utility demand charges, the maddening 36-month delays caused by the AI supply chain wars, and the brilliant workarounds currently defining the space. From BS-buffered megachargers doing molecular arbitrage, to off-grid thermal pods, to AI vision robots plugging in autonomous cars.
The infrastructure is mutating in real time to survive the realities of the grid. And looking at all these trends, it really leaves us with one highly provocative final thought to consider.
Let's hear it.
If the near future is defined by decentralized mobile power pods, curbside taps woven directly into urban buildings, and autonomous batteries that physically drive up to your self-driving car to charge it while you sleep, will the traditional gas station real estate model completely collapse?
Oh, wow.
We might actually be watching the physical spatial act of driving somewhere specifically to refuel become entirely obsolete.
That is a staggering shift to think about, a world where the fuel just comes to you. Well, thank you for joining us on this deep dive into the source material. We'll catch you on the next one.